Good morning, student. In this video, I will be teaching you group 14 elements. So let me discuss the synopsis of group 14 elements. So group 14 elements are carbon, silicon, germanium, tin, lead. So you can remember the trick, koi si geet sunao pyar wale. You can remember the trick, koi si geet sunao pyar wale. Carbon is very widely distributed in nature, and it is essential constant of all living matter. So our life is carbon based. Our life is carbon based. It is also present in proteins, carbohydrates, fats, etc. So carbon is very essential element. There is no organic compound chemistry without carbon. So carbon chemistry, carbon compounds chemistry are studied in a separate branch of chemistry. We call it organic chemistry. Silicon is second most abundant element on Earth crust. So you have to know that the most abundant element is oxygen, second is silicon, and third is aluminum. So most abundant metal is aluminum, second most abundant element is silicon, most abundant element is oxygen. Very pure silicon is required for electronic industries like transistor, computer chip. You must be aware that silicon, germanium, these are used to prepare semiconductors. Semiconductor industry has powered the growth of technology, particularly the computer chips, transistor, these are. Germanium is not well known. Germanium is not well known, but its uses are ultra pure germanium is used for semiconductor industry. Tin and lead are common elements due to their easy extraction methods. So tin and lead are metals. Lead is a toxic metal also. The general configuration of group 14 element is NH2-NP2. The general configuration of group 14 elements are NH2-NP2. So carbon is 6. So it is 1s2, 2s2, 2p2. So this is the general configuration of carbon. Silicon is, you can also write carbon configuration. You can use 1s2 for helium. So you can also write helium 2s2, 2p2. So this is also the way to write the electronic configuration. Now coming to silicon, silicon is 14, neon 3s2, 3p2. This way you can write the configuration. So the number of electron present in the penultimate set. So in the penultimate state of carbon is 2. So in the excited state, what happened? Carbon 2s electron goes to 2p. So it becomes 1s2, 2s1, 2p3. So it shows tetravalency. Carbon shows tetravalency. It forms 4 bonds around itself. This is the Lewis dot structure of carbon. This is the Lewis dot structure of carbon. Now, the number of electron in penultimate cell of silicon is 8, but in germanium, tin, lead, it is 18 electron. Due to this difference in their electronic configuration, carbon and silicon are different from other elements. So carbon and silicon are different from other members of the element. And they have a special property that we call it inert pair effect. They have a special property that we call it inert pair effect. Carbon and silicon are widely distributed, and tin and lead compared to tin and lead. So carbon and silicon are dominant than tin and lead. Extent of occurrence. So silicon is the most abundant, then carbon, then tin, lead. Then this is the abundance of these elements. Tin stone, cassiterite, tin stone, SnO2 is SnO2, that is tin 4 oxide is also called cassiterite. Galena is PbS, lead sulfide. Cerussite is lead carbonate. Cerussite is lead carbonate. Anglesite is lead sulfate. Anglesite is lead sulfate. Ultra pure form of silicon and germanium are used to make transition that I have already discussed. Ultra pure means purity of higher order. Higher order purity is required. Now, oxidation strength trades in chemical reactivity. So from carbon to lead, the non-metallic nature decreases and metallic. As you know, carbon, silicon, germanium, tin, lead, from top to bottom, metallic character increases. From top to bottom, metallic character increases, non-metallic character decreases. So carbon being non-metal, silicon, germanium being metalloid, tin and lead being metals. Carbon and silicon are non-metal. Sometimes some book writes silicon as non-metal, but it has some metallic property also. So it is treated as metalloid. Now, germanium is a metalloid, tin and lead are metals, melting points. So the melting point ranges in the order carbon greater than silicon, silicon greater than germanium, germanium greater than lead, lead greater than tin. Boiling point order is carbon greater than germanium, greater than tin, greater than silicon, greater than lead. Now density decreases from carbon to silicon and then increases from silicon. So these are the things that you need to remember. Density order is lead has the maximum density, then tin, then germanium, then carbon, then silicon. Bond energy. Bond energy of carbon bond is more as compared to silicon, then germanium, then tin, then lead. The first ionization enthalpy of carbon is more than silicon, more than germanium, more than tin, but tin is less than lead. The second ionization energy of you can say carbon is greater than germanium, greater than silicon, greater than lead. So these you have to remember. So ionization energy sequence you have to remember. How you remember, or you can easily do with the writing electronic configuration. So when you write the electronic configuration, you will get how this varies. The element with highest ionization energy in 4 is, so the element with the highest ionization energy is carbon, carbon being a non-metal. So non-metal has high ionization enthalpy. The very high ionization of carbon is due to small size. So carbon is small size and it has high electronegativity. It has high electronegativity. And this also results into its non-metallic character. Electronegativity of carbon is 2.5. Electronegativity of silicon, germanium are in the range of 1.8. So common oxidation state of group 4 is +2 +4. Like carbon monoxide, it is +2. Carbon dioxide, it is +4. C3O2, the oxidation state of carbon is +3, 4/3. So this, if you see the structure of this compound, this is called carbon suboxide. So the terminal carbon, these two carbons are +2 +2, and the intermediate carbon is 0. So the total 4 subdivided in 3 carbon. The reluctance of NH2 electron to participate in bond formation. The reluctance of NH2 electron to participate in bond formation is known as inert pair effect. So this is called inert pair effect. This you have to remember, student. Now, so carbon and silicon generally don't show the +2 oxidation state, but few compounds are there like carbon monoxide. So, but it is shows means a typical type of structure. Okay. +2 state gradually becomes more stable down the group, and +4 stability decreases, and this is due to inert pair effect. This is due to inert pair effect. This is due to inert pair effect. So keep this in mind. So in carbon monoxide, you will find that there is a coordinate covalent bond, and the oxidation will not consider +2. You can take it +2, but since it has some special bond, that's fine. The element in the group are relatively unreactive, but reactivity increases. As we know, reactivity increases down the group. So lead is less reactive due to surface coating of oxide. So on the lead surface, the surface coating of lead oxide is formed. That's why lead is less reactive. Carbon, silicon, germanium are unaffected by water. So carbon, silicon, germanium are unaffected by water. Tin reacts with steam to give tin oxide and hydrogen gas. So important, tin reacts with steam to give hydrogen gas and tin oxide. Lead is not affected by water due to oxide layer. So lead is not affected by water due to oxide layer formation. Due to oxide layer formation. Now, tin and lead dissolve readily in nitric acid. So lead will give you lead nitrate, nitric oxide, and water. Carbon is unaffected by alkalis. Carbon is unaffected by alkalis. Silicon react with alkalis to give silicate. So silicon reacts with alkalis to give silicate. Tin and lead also react with alkalis. So when lead reacts with NaOH, it forms sodium silicate. When tin reacts with NaOH, it forms sodium stannate. When lead reacts with NaOH, it forms sodium plumbate. Here, this is the reaction of silicon. So here correction is required here. So this is silicon. So when silicon reacts with NaOH, it forms sodium silicate. When tin react, it forms sodium stannate. When lead react, it forms sodium plumbate. So Hydrolysis of sodium stannate gives this complex compound. This you have to remember. The reactivity of a Gaussian element in group 14A, 4A of halogen follows. So fluorine will be more reactive than chlorine, then bromine, then iodines. Hydrides. Carbon forms large number of hydrides. These hydrides are called hydrocarbons. These hydrocarbons are of two types, saturated hydrocarbons and unsaturated hydrocarbons. Silicon form limited number of hydrides and silanes, like silicon hydride, SiH4. Hydrides of carbon are more stable since electronegativity of carbon and hydrogen nearly same. So hydrides of carbon are more stable. Hydrides of carbon are more stable. Hydrides of silicon are less stable because in silanes, hydrogen withdraw electron from silicon hydride hydrogen bond. So hydrides of silicons are less stable. Silanes are good reducing agents. Silanes are good reducing agents and they undergo hydrolysis in alkaline medium. They undergo hydrolysis in alkaline medium. The element of 4A group form tetrahalides of the time MX4. So they form tetrahalides. PbI4 does not exist because pi bond initially formed during the reaction does not release enough energy to unpair 6s2 electron. So lead tetraiodide is it does not exist. Lead tetraiodide does not exist because lead iodide bond initially the bond which is formed does not release enough energy to unpair the 6s2 electron. Example of tetrahalides are CCl4, SiF4, SiCl4, SnCl2. CCl4 is called carbon tetrachloride, SiF4 is called silicon tetrafluoride, SiCl4 is called silicon tetrachloride, SnCl4 is called tin tetrafluoride. The thermal stability of tetra, this is important question. So thermal stability decreases. Carbon tetrahalides are more stable than silicon tetrahalides. Silicon tetrahalides are more stable than germanium tetrahalides. Germanium tetrahalides are more stable than tin tetrahalide. Tin tetrahalides are more stable than lead tetrahalides. These halides are covalent compounds only. These halides are covalent compounds only. So they are covalent in nature. CCl4 does not undergo hydrolysis because there is no presence of 1s2, 2s2, 2p2. There is no 2d, so there is absence of vacant d orbital. So CCl4 will not undergo hydrolysis. This is a very important question which has been asked in competitive exam. Silicon tetra will undergo hydrolysis due to presence of vacant d orbital. Silicon do have vacant d orbital 1s2, 2s2, 2p6, 3s2, 3p2. So 3d is vacant here. So vacant orbital it has. So it will take the accept the lone pair from water. Water acting as ligand here. Oxide. Carbon forms two oxide, carbon dioxide and carbon monoxide, while silicon forms silica, SiO2. Both CO2 and Si2 are acidic oxides. So keep in mind that metal oxides are acidic in nature, whereas non-metal oxides are basic in nature. Okay. And some of the metalloids oxides are amphoteric. The acidic nature of oxide decreases. So carbon dioxide is more acidic than silica, SiO2. Silicon oxide is more acidic than GeO2. GeO2 is more acidic than SnO2. SnO2 is more acidic than PbO2. Now, let's see the difference between CO2 and SiO2. So CO2 is a gas, whereas SiO2 is a solid. It is linear with double bonds. It has a three-dimensional structure with single bond. It is more acidic. It is less acidic. Low melting point due to weak attractive force. It is high melting point due to giant structure. So it has a giant structure. And in the giant structure, if you see the structure, then silicon is bonded with 4. So its coordination number of silicon will be 4 here. Now, anomalous behavior of the first element. Why first element so anomalous behavior? Let me discuss the first why the first element shows anomalous behavior. First element, carbon shows dissimilarities with other element of the group. Carbon is widely distributed in nature. Carbon occurs in free state as well as other elements may not generally not available to a larger extent. Carbon has no vacant d orbital, but other elements vacant d orbitals are present. So octet expansion will not take place in carbon, but in other element expansion of octet take place and coordination number increases from 4 to 6. Coordination like SiO4 react with 2 fluoride and to give SiF6. So here the coordination number of silicon is 6. Here the coordination number of silicon is Silicon coordination number is 6. Carbon shows maximum valency of 4 and other elements show maximum valency of 6. Carbon can form covalent bonds, covalent compound, because it is a non-metal and small atomic size. Carbon has more capacity to form chains, so carbon show maximum catenation property and due to higher strength of carbon. This was also asked in IIT. So they did not ask in kilojoule per mole, it is kilojoule. They asked in approximately 100 kilocalorie per mole they gave. So this was IIT question. Silicon can form longest chain with 8 silicon atoms. So they can form a longest silicon chain. Carbon along form multiple bonds. So carbon can form double bond, triple bond, etc. So carbon form triple bond with nitrogen. Carbon can form double bond with itself, can bond triple bond with itself. It can form double bond with oxygen as well as sulfur. Thermal stability of methane is more than selene. Selene is more than germane. Germane is more than tin hydride. Tin hydride is more than lead hydride. Hydrates of carbon are called hydrocarbons and they have more thermal stability to high dissociation temperature because they have higher bond enthalpy. So that requires high temperature to dissociate. The difference in stability between alkanes and other hydride is due to difference in electrons. So the difference in stability between alkanes and other hydride is due to difference in, more is the difference in electrons, the easier it is. The thermal stability of hydride is inversely related to the reducing capacity of hydride. So more is the reducing capacity, lesser will be the thermal stability of the hydride. Catenation. It is called self-linking property. Catenation is called self-linking property. Self-linking property. The linkage of same atom with each other to form long chain ring is called catenation. So this is very prominent in case of carbon. Catenation is only possible if the elements are either divalent or polyvalent. So catenation is only possible when the elements are divalent, can form 2 bonds or many bonds. Catenation is not possible in with exhibit valency less than 2. So catenation is not possible for univalent elements. The element with highest catenation property is carbon. So carbon shows maximum catenation property. And this is due to high bond dissociation energy. This is due to high bond dissociation energy. I have already discussed the bond dissociation. The order of catenating power. So this can be an important question. Carbon shows maximum catenation, then silicon, then germanium, tin, then lead. Lead has very less catenation. The property catenation is responsible for the formation of this is the property which is actually responsible for the formation of large number of organic compounds. So carbon takes the top position as far as catenation properties. So general formula of selene is SiNH2n plus 2, where n can be up to 8. Germans have the general formula GnH2n plus 2, n equal to 5 maximum. So similar, like alkane have a general formula CnH2n plus 2. Similarly, selenes and Germans are formed by silicon and germanium respectively. So this you have to keep in mind, student. Now, allotropy. The existence of an element in more than one form is called allotropy. As you know, carbon shows so many allotropic forms like diamond, graphite, Buckminster fullerene, C60. The phenomenon of element existing in 2 or more physical form having similar chemical properties, but different physical properties are called allotropy. So allotropy is due to difference in structure or arrangement of atoms. So carbon shows 2 types of allotrope. One is the crystalline allotrope, another is the amorphous allotrope. Crystalline allotropes of carbon are diamond and graphite. Keep in mind that in diamond, the hybridization of carbon is sp3, but in graphite, the hybridization of carbon is sp2. In Buckminster fullerene C60 also it is sp2. The amorphous form of silicon coal are, the amorphous form of carbon are coal, coke, it is not cake, it is coke, wood, charcoal, animal charcoal, lamp black, gas, carbon, petroleum, coke, sugar, charcoal, etc. Except lead, remaining all 4A group elements exhibit allotropy because lead is a metal. So lead will not show allotropy. Other elements, diamond, the hybridization of carbon is sp3. One carbon is surrounded by 4 other carbon. Diamond has giant polymer structure in which each carbon atom is tetrahedrally joined by 4 other carbon atoms. So this was about diamond. This is the structure of diamond, 3-dimensional structure with carbon-carbon bond length of 1.54 angstrom, or you can say 154 picometer. Keep in mind that 1 angstrom is 10 to the power minus 10 meter, and 154 picometer is 10 to the power picometer is 10 to the power minus 12 meters. So keep this in mind. These are conversion factors. Diamond is the hardest known naturally occurring substance. The carbon-carbon bond length is 1.54 angstrom. The bond angle in diamond is 109. That is tetrahedral. Melting point of diamond is very high. It is 42. So it's very high. Density of diamond is 3.5 gram per cc or centimeter cube. Diamond glitter due to high refractive index. It has the highest refractive index of any substance, almost 2.42. 0.45 here it is written. Diamond is non-conductor of electricity because of absence of free electrons. So diamond is a poor conductor. It is an insulator. It is stable up to 1500 degree in vacuum, but 18 to 2000 it converts into graphite. So at a very higher temperature it converts to graphite. The quality of diamond is expressed in terms of carats. So Kohinoor diamond is 186 carat. Pitt diamond is 136.25 carat. Pitt. Keep in mind that 1 carat is equal to 200 milligrams. So this you have to keep in mind. Now, uses of diamond. As we all know, diamond is a very precious stone. It is used in jewelry, for drawing thin wires, for cutting glass, drilling rocks, as an abrasive, for sharpening of instrument. So these are the uses of diamond. Now coming to graphite. So graphite is prepared by a Chanson process. Silicon carbide is obtained with sand and coke are heated at higher temperatures. So silica treated with coke forms carbon monoxide and silicon carbide. Silicon carbide is a covalent solid. Silicon carbide is a covalent solid. Carborundum is hitting gives graphite. So carborundum, this is also called carborundum. Carborundum. So when it is heated, it gives silicon and carbon or graphite. In graphite, carbon has sp2 hybridization. Graphite has two-dimensional layer structure. It is thermodynamically most stable electron. So keep in mind that thermodynamically graphite is the most stable electron. It has double bond character. Electron can free electrons is there, mobile electron. That's why it is graphite is a good conductor. Graphite is a good conductor. Graphite is a good conductor. So thank you, student, for watching this video. I tried my level best to explain you group 14. Rest part of the video will be covered in my next lecture. Thank you.